Hi everyone, this is Mrs. Poland. This is the first lesson of Unit 8, Chapter 11, and we're investigating something called the chi-square distributions. It's a series of different tests, and the first one we're going to do today is the chi-square goodness of fit test. I hope you remember this sponge guy. So for the chi-square distribution, again, the one we're doing today is called the chi-squared. So instead of writing it chi-squared, we write it this way. And it's called the chi-squared goodness of fit test. And we use it when we're comparing an observed distribution to what is either known or what is given. So M&M Mars says that its M&Ms follows the following distribution: 13% brown, 14% yellow, 20% orange, 16% green, 24% blue, and 13% red. We're not quite sure if this is true anymore, so we investigate. So ideally, we would be in class and I would be bringing in gobs and gobs of M&Ms. So to get the feel of it, send your parents out to buy some M&Ms. So let's pretend that we had this huge amount of M&Ms in class and you're sorting it out. 53 of them were brown, 43 were yellow, 110 were orange, 57 were green, 141 are blue, and 57 are red. So the first thing we want to do is find out how many M&Ms are in the sample. So we're going to add all these delicious M&Ms together. And when we do that, we have 461 M&Ms. So the null hypothesis is that the claimed color distribution is true. And again, you want to put color distribution because you want to get the context of the problem in. Probably be better to say the claimed color distribution of the M&Ms is true. Alternative is that the claimed color distribution is not true. So we want to see if the observed M&Ms are around this type of percentage for each color category. Again, color is a categorical data, and when you're dealing with a chi-square distribution, you're specifically dealing with categorical data. So the first thing we need to do is we want to figure out how much we would expect to get based on this distribution. So what you would do is you would take the amount in the sample and multiply it by each of these percentages. So for the brown, you would take the total of 461 and multiply it by the 13%. And when you do that, you get 60 brown M&Ms. To get the number of yellow, you would take 461 and multiply it by the 14. And when you multiply 461 times 14, you get 65. I'd like you to do the same thing with the other four. I'll put the video on hold. Check to see if you match my answers. The blue I had to round down because when you add up the total, it should add to the 461, so you may have to readjust the rounding. We're going to calculate the chi-squared statistic by hand for today's lesson. So I set up a chart for this particular problem, observed or expected count. So we're going to take the expected counts and putting into the column next to the observed. Again, both the observed and the expected column will both add to 461. and you may have to adjust your rounding. The chi-squared statistic is actually given to you, and it's equal to the summation of the observed minus the expected squared divided by the expected. And you'll see that on your formula sheet. So we're going to calculate this by hand. Observed minus expected is -7. 43 minus 65 is -22. 110 minus 92 is 18. 57 minus 74 is -17. 141 minus 110 is 31. And 57 minus 60 is -3. And again, this is 18. We're then going to, after you subtract the two, square it. So this is 49. -22 squared is 484. 18 squared is 324. 17 squared is 289. 31 squared is 961. -3 squared is 9. Okay. Then we're going to take each one of these terms and divide it by the expected. So 49 divided by expected. And I'm going to round to 3 decimal places. 484 divided by 65. I'm going to put the video on hold. Can you finish up the other pieces? Finally, you're going to take all these components, they're called chi-squared components, and you're going to add them up. And you get 24.576. What value would we get for the test statistic if our sample was very close to what was expected? It would be a value close to 0. What value would we get for the test statistic if our sample was very far from what was expected? A very large number. So I'm going to show you in a few minutes how we can determine how the 24.576 relates to our null and alternative hypothesis. But first, let me go into a little bit more about the chi-squared distribution. The chi-squared distributions are a family of density curves that take on only non-negative values and are skewed to the right. So all of these are chi-squared distributions. The lowest value it could be would be 0, and it goes on infinitely far to the right. Since it's a density curve, the area under the curve has to equal to 1. And the chi-squared distribution is based on degrees of freedom, but it's a little bit different than the t-distribution, and I'll go more into that in a minute. So the higher the degree of freedom, the more and more normal-like it looks, though it will never be totally normal-like. For the chi-square goodness of fit test, the degrees of freedom is the number of categories minus 1. So for our particular problem, let me make it a different color. The degrees of freedom are based on the number of colors. And since we have, I guess I should do it up here. Since we have 1, 2, 3, 4, 5, 6 colors, the degrees of freedom is going to be 6 minus 1 or 5. So we want to find the p-value for our distribution. Again, it's skewed to the right. Here's 24.576. What is our likelihood of getting a test statistic of 24.576 or larger? So in this area. So the probability that a chi-squared statistic is greater than 24.576, and there's something called the chi-squared CDF, chi-squared distribution. The low value is 24.576. The high value is 9.9E999. And the degrees of freedom is 5. Access it, you would do menu, statistics, distributions, chi-squared CDF. The low would be 24. Oh, here's the point. Hold on. 0.576. And now we're going to do 9E999. And then the degrees of freedom is equal to 5. Hit OK. So there's our p-value. So this is equal to 0.00017. And again, that's our typical p-value. And we didn't establish an alpha, but let's pretend we did in the beginning and said it's equal to 0.01. This p-value is certainly less than 0.01. So since our p-value is less than 0.01, since our p-value is less than 0.01, we reject HO. There's convincing evidence that the claimed color distribution is not true. I'll be doing a second video on this lesson, so look out for it.